Okay, so the obvious basis in which to calculate this expectation value is the basis of eigenstates of the Hamiltonian. So supposing we have eigenstates of the Hamiltonian, so these are the eigenstates and this is the eigenvalue. And the lowest eigenvalue by definition is going to be j equals 0. Now let's expand our state. We know that our state can be expanded in terms of these eigenstates, and we can do that explicitly by popping in the identity operator, just to practice doing that. Don't forget to use a different dummy index the next time you substitute in. Now the Hamiltonian acting on these states is very simple. We can take all the sums out. This is the inner product between psi and the eigenstate, which we will call Cj star. H acting on this is going to give us out an Ek, and this is going to give us a Ck. So this is the definition of Ck, and so that's Cj star. Now the inner product between two orthonormal states is the delta function, which means we can get rid of one of these sums, and so it's just the weighted sum of the energies, as we'd expect, weighted by the probability of having that energy in that state. And of course this is strictly greater than or equal to, because E0 is by definition the lowest of those, and sum of all the probabilities is equal to 1. And so we've trivially proved that this expectation value is greater than or equal to the ground state energy. So what good is knowing this result? Well, technically, all you have to do is try every possible wave function, and whichever one gives you the lowest energy, the lowest expectation value of that, is the ground state. Done. Of course, trying every wave function in an infinite dimensional space is a bit hard. So what we do in practice is we try a good shape and optimize. So ansatz is just a German word that makes it sound a little bit less dodgy when you're guessing. But what you do is you make an ansatz that depends on some parameter. And so you might have a parameter alpha describing the width of a bump if you've got a bump. And then what you do is you optimize, you find this expectation value of the Hamiltonian, and you find the value for alpha that gives you the lowest energy, and that's your best guess. And so as you get better and better ansatzes, and as you optimize, you're lowering and lowering your upper bound on the ground state energy, all of which may seem a little abstract, so let's do an example. And let's go back to the physicist's friend, the harmonic oscillator. Now the harmonic oscillator, in one dimension, has that Hamiltonian, and it's a single component wave function in space. Now what we have to do is we have to guess a form for this wave function that might be a bit like the ground state of that. Now obviously when we have very large x, this value is going to get very large, this potential energy is going to get very large, and when we have very large momentum, that's going to get very large. So what we want is something that doesn't change its phase very much in the position basis, so that it has low momentum, and we want something that's quite near the middle. So let's have a bump. Now your classic kind of bump would be something like a Gaussian. So our trial wave function will look like a Gaussian, and the Gaussian is going to have some width that we don't know, so we'll just use the parameter b to parameterize that, and we need this wave function to be normalized. So if we take this and we mod square it, which just gives us a 2 there, and we take the integral, and then take the inverse square root of that, then we can find that in order to get this normalized, we need a factor, and therefore our wave function, our trial wave function, is going to be a function of x and b. Notice how I'm deliberately using different variables here inside the wave function so you don't get too attached to one variable or another, which helps you a lot when you're using them as dummy indices. So now I have to calculate the expectation value of the Hamiltonian, which we understand well on the position basis. There we go, and then we have to plug in for our wave functions, which would be as good time as any to just plug this into Mathematica. So Mathematica would do the derivatives for you, and then it would do the integrals. The problem with that, of course, is that you're not going to have Mathematica. You should be able to take derivatives of exponentials by yourself. You should be able to take derivatives and do product rules and so forth by yourself. In general, in an exam, if I have some Gaussian integrals or some funky integrals, I will give them to you, but you're going to have to build this into the pieces of the integral that you're going to want. Okay, so I'm going to plug this into Mathematica. So here's my wave function. I'll just run that. And then just to show to you that this is the right normalization constant, equals 1. And now coming down here, I've got my wave function, my derivative of my wave function, my second derivative of my wave function, and my potential term. And I'm integrating all of those. And I get this result here. And so the expectation value obviously depends on b. And clearly, if b is very large, then this term is small, well this term is large, and vice versa. If b is very small, then this gets small, but this gets very large. So there must actually be an optimal value of b. What's the value of b that gives us the least of this? Well, what we do is we take the derivative. So the derivative of this with respect to B. And we set the derivative to 0. And so now we've got the optimum value of B. If we plug that back into here, we get h bar omega on 2, which is the exact result. What do I mean by the exact result? That's not just an upper bound for the ground state energy, it's the actual ground state energy. So it's the least upper bound, it's the final result. Why did that happen? That happened because I was so clever I tried a Gaussian, and in fact the ground state of the harmonic oscillator is exactly a Gaussian. So, in some sense, I cheated. On the other hand, one bump that looks about the right width is going to look very much like another bump that looks exactly the right width. So if I get a sort of bumpy Gaussian looking thing, I will get very close to this result anyway. Now let's try a second example. The ground state of the hydrogen atom. Okay, this is a little bit more complicated because it's in 3 dimensions. On the other hand, you can probably guess that the ground state is going to be spherically symmetric. So have a go, just try it really cold, try and come up with your own trial function and have a rip.